Bismillahirrahmanirrahim. Unit 12 Geometrical Optics, Numerical Problems, Physics 10 National Book Foundation. In geometrical optics, there is usually one aspect which is not very clear to the students, and that is what is virtual image and what is a real image. How are these formed? When are these formed? So a real image is an image which is formed on the path of the light. Now, this explanation is not given in the books the way I am telling you. So please be with me, listen to me very carefully. Path of light means when a light ray strikes the mirror, it returns back to the same medium. That is the natural path. It does not enter the mirror. So an image formed inside the mirror is virtual image. And if an image is formed in front of the mirror, that is a real image. Same is the case with the lenses. Light enters a lens and it passes through it and goes to the other side. That is the natural path. If the image is formed on the other side of the lens, it is a real image. And if the image is formed on the same side as the light is coming, that happens in case of concave lens. That is a virtual image. Virtual images are always erect. Real images are never erect. Real images are always inverted. All right. Now coming on to this problem 1, I'll keep explaining these aspects in almost all the questions that I will solve next, wherever it comes. So be with me, try to understand, and if you have a question, put it in the comments. I'll be addressing these problems separately with individuals if at all I need to. Okay, now coming on to this problem 1. We have a concave mirror with radius given as 15 centimeter. Since radius is the radius of the spherical mirror, half of the radius is the focal length. We need the focal length for this location of the image. So we find the focal length first. Since focal length is r by 2, therefore f is equal to 15 by 2, which is equal to 7.5 centimeter. And the distance of the object is 10 centimeter. To find the location, nature, magnification and height of the image, find the location using the mirror equation. This is the mirror equation. And in mirror equation, you must have come across this equation as well, which is given in some other books, like your Punjab textbook board book, which is 1 over f is equal to 1 over p plus 1 over q. Here p is same as distance of the object and q is same as distance of the image. So you may use these symbols or letters p and q for distance of image and object, or you may use p and q, it doesn't matter. But don't mix it up. You don't have to get confused. Distance of object and distance of image are equally good as p and q. So here, since I need to find the distance of the image, I separate this from the distance of the object, moving distance of the object 1 over do to the other side and swapping these sides. Taking the LCM d naught f and d naught minus f. Since it is 1 over di, I take the reciprocal and di is equal to d naught f over d naught minus f. Now substituting the values, 10 is my distance of the object, 7.5 is my focal length, 10 minus 7.5 in the denominator. This makes it 75 over 2.5, which calculates to 30 centimeter. So the distance of the image is 30 centimeter from the mirror. It is positive distance. If the image distance and the focal length have the same sign, positive or negative, then both are on the same side of the mirror. Now, like I said, distance of the image is positive. Focal length is also positive. That means both are on the same side. And you know that for a concave mirror, The focal length is in front of the mirror. It is on the same side where the light is coming. Since the distance of the image is also positive and it is on the same side, that means image is formed on the same side as that of focal length. And if an image is formed on the natural path of light, it is a real image, since natural path of light for the mirror is light falling on the mirror and then reflecting back into the same medium. That is a natural path. So this is a real image. So nature of the image is real image is formed in front of the mirror. Real images from a single mirror or lens are always inverted. I said real images from a single mirror or lens are always inverted. Okay. Image formed here is 30 centimeter tall and from 30 centimeter from the pole and is real and inverted. All right. Magnification. Magnification is given in your book as di, distance of the image divided by distance of the object, or at the same time it is either hi, height of the image, or height of the object. Either one of them can be used for the M magnification. So here, since I have distance of the image and distance of the object, I first find the magnification, that is 30 over 10 is equal to 3. So magnification here is 3. I will use this magnification of 3 with hi over h naught to find the height of the image. So height of the image is hi over h naught is equal to 3. Hi is equal to 3h naught. I have the height of the object, that is y is 90 cm tall. I put 90 for h naught and hi, height of the image is 3 into 90, which is 270 centimeter. Okay, problem 2. A 5 cm tall lighted candle is placed 12 cm from convex mirror of focal length 6 centimeter. Find the location, nature, magnification and height of image. Here it is a convex mirror. We need to find the location, nature and magnification of the image. So remember, in a convex mirror, the image is always formed behind the mirror. It is always a virtual and erect image, and it is always a diminished image, a smaller image. So we will see it further. And right now, let us have the data. That is the distance of the object. Candle is 12 centimeter away. The focal length is negative 6 centimeter. That means focal length is behind the mirror. Okay. Height of the object. The candle is 5 centimeter tall. Mirror equation is given as 1 over f is equal to 1 over d object plus 1 over d image. Here I would like to emphasize that since we need to find the distance of the image, we should not be proceeding with all the calculations here. First, write the mirror equation on the side lines, on the side working, calculate the distance of the image like I did it here, and you know all these steps. I did it in the previous question as well, and then take these final equation to the main body of the question. This helps checker and examiner, and it reduces their time. If they are interested to see all these steps, they may see, otherwise they may proceed and save their time. Substitute the values here. So minus 6 into 12 divided by 12 minus 6. This minus 6 makes this thing as positive. So minus 72 over 12 plus 6, which is equal to distance of image is equal to minus 72 over 18, which is minus 4 centimeter. The distance is inside the mirror and it is 4 centimeter away. Now convex mirror always forms a virtual image, right? Virtual images are always erect or say never inverted. Sign of the distance of image is same as focal length. This showed that both are on the same side of the mirror. Okay. Magnification of the convex mirror. Remember, convex mirror magnification is always less than 1 and it always forms a smaller image, a diminished image. So magnification is negative of distance of image over distance of the object. It is taken as negative. The magnification of convex mirror is taken as negative, or it is also equal to height over height of the image over height of the object. Magnification is negative of -4 over 12. These two minus makes it positive and it becomes 1 over 3 or 0.333. Now height of the image is to be found. So height of image over height of the object is equal to 1 over 3, taking h height of the object on the other side, substituting the value of 5 here, this height of the candle 5 centimeter, and calculating it gives approximately 1.67 centimeter. Problem 3. A girl standing near converging mirror of focal length 15 centimeter. Where should she stand to get a real inverted and 3 times enlarged image? And B is a virtual erect and 2 times diminished image. Now, since it is a converging mirror, f is taken as positive 15 centimeter. Magnification is given as 3, and we need to find the distance of the object. Where to place the distance of where should the girl stand? So magnification in terms of the distances is given as distance of the image divided by distance of the object is equal to m. Since m is equal to 3, di over do is equal to 3, and we can write it as di is equal to 3 times distance of the object. Now substitute the values in the mirror equation. 1 over f is equal to 1 over do plus 1 over di. Here I substitute the values as f is equal to 15. Do I need to find, plus 1 over 3 do I substitute for di from here. Okay. Now 1 over 15 is equal to 1 plus 3 over 3 do, which makes it 1 over 15 is equal to 4 over 3 do. I need to find this do. I move this do to the other side, and this becomes as a numerator here, and 15 to this side, and it is cross multiplied here. So it becomes do is equal to 4 times 15 divided by 3. I cut this 15 with this 3, which makes it 5, and this is 4 times 5 equal to 20 centimeter. So the girl should stand 20 centimeter from the mirror to make an image which is 3 times bigger than her height. Okay. Now the part B is virtual, erect and 2 times diminished image. Notice that this is a converging mirror. A converging mirror never makes a virtual image which is diminished. A converging mirror always an enlarged image. So this question has some problem here. It will never make a diminished image. If it is diminished, this cannot further be solved. This is the final solution. However, I would like to do it with the enlarged image, and I would do it as diminished is cut. I cannot do it with diminished. I write it as enlarged image, and we solve it for virtual and enlarged image. Now, since it is a virtual image, di is negative. Distance of the image will be negative. It will be inside the mirror. So it is minus di over do. So this can be written as di is equal to minus 2 do, negative of 2 d distance of the object. Now again, putting these values into the mirror equation, 1 over 15 is equal to 1 over do plus 1 over negative 2 do. Now writing this negative into this here, changing this plus sign, 1 over 15 is equal to 1 over do minus 1 over 2 do. Taking the 2 do as LCM, 2 minus 1 is equal to, this makes it 1 over 15 is equal to 1 over 2 do. Taking this do to the other side, and 15 to this side will give us do is equal to 15 over 2, which is equal to 7.5 centimeter. This is the answer given in the book. Probably book has an error of writing it diminished here. It should have been enlarged for this answer. Problem 4. Light ray enters from air to water. At angle of incidence 30 degrees. Here the refractive index of water is given as 4 by 3. Find the angle of refraction in water. The second part of this question is, if the light ray travels from water to air at angle of incidence of 40 degrees, then find the angle of refraction in air. So just note that air is a rare medium, water is a denser medium comparatively. So here if the angle of incidence is 30 degree, the angle of refraction has to be less than 30 degrees. Just keep it in mind. Secondly, in order to find the angle of refraction in water, first we get the data. Angle of refraction of water is equal to 4 by 3 and angle of incidence is equal to 30 degrees. Now recall the Snell's constant, that is sine of theta 1 divided by sine of theta 2. That is, the theta 1 is the angle of incidence, theta 2 is the angle of refraction. That is a constant. And it is the ratio of the indices of the refraction of the two media, that is n2 over n1. This is written as sine theta 1 over sine theta 2 equal to n2 over n1, and this relation is generalized as n1 sine theta 1 equal to n2 sine theta 2. Now here in this case, since air is the first medium and water is the second medium, n1 is equal to na, refractive index of air, which is equal to 1. n2 is the refractive index of water, which is given as 4 by 3. Theta 1 is the angle of incidence and theta 2 is the angle of refraction. Now, using these notation in this general equation, we get NA sine of I equal to NW sine of angle R. Now, since we need to find the value of angle of refraction, we swap sides. So, NW sine of R is equal to NA sine I. Sine R is equal to 1 over NW sine of angle I. Since NW is given as 4 by 3, the 1 over NW will be 3 by 4. That is the reciprocal of 4 by 3. Now substituting the value of angle of incidence, that is 30 degrees, sine R becomes 3 by 4 sine of 30 degrees. Now putting this sine of 30 degree equal to 1 over 2, the sine of 30 is 1 over 2. So sine of R becomes 3 by 4 into 1 by 2. Calculating this returns in 0.375. Now to calculate R, take this sine inverse of 0.375. Using a calculator, you will find it approximately 22 degrees. Now this second part. Now second part of problem 4, if the light ray travels from water to air at angle of incidence of 40 degrees, find the angle of refraction in air. Here, note, water is a denser medium, air is a rare medium. The ray of light from dense to rare medium will bend away from normal, making an angle greater than angle of incidence. Here, the angle of incidence is 40 degree. The angle of refraction has to be greater than 40 degree. Just keep it in mind while making your calculations so that you know your answer has to be greater than 40 degree. Don't make an error in it. So when water is medium 1 and air is medium 2, we get this generalized equation as NA sine of R, second medium, air, refractive index times sine of R equal to the first medium angle of incidence, and that is water. Light travels from water to air. So these are the substitutions we are making, and values into this equation. 1 sine R is equal to 4 by 3 sine of 40. Now sine R is equal to 4 by 3 into 0.643. This is the value of sine 40. Making this calculation results in sine R is equal to 0.857. This is an approximate value, remember. Now, in order to calculate R, we make sine inverse of 0.857, which is approximately equal to 59 degrees. And that is the angle of refraction in air when light moves from water into air. Problem 5. Light ray is incident from core n is equal to 1.42 to cladding n is equal to 1.33 on core cladding interface. Find minimum angle at which total internal reflection takes place. Notice, for total internal reflection to take place, the light must travel from denser medium to the rare medium. This is a case of an optical fiber which has a core of a denser medium and a cladding around the core made of rare medium. In this case, N1, the refractive index of core is 1.42, the denser medium, and N2, refractive index N is 1.33, the rare medium. We need to find the angle theta, the critical angle at which beyond which the total internal reflection takes place. Remember, theta critical is the angle at which the light reflects at 90 degree from the normal. Beyond this angle, the total internal reflection takes place. So we first calculate the theta critical, and we would know that any angle beyond theta critical would be the total internal reflection angle. Formula for the theta critical is sine inverse N2 over N1. Substitute N1 and N2. We get theta critical equal to sine inverse 1.33 over 1.42. Calculating 1.33 over 1.42 results in 0.9366, and calculating sine inverse 0.9366 gives us the critical angle approximately 69.5 degrees. So any angle beyond this, or the minimum angle, is 69.5 plus to get a total internal reflection. Problem 6. A boy is looking at a pen through a concave lens of focal length 10 cm. What is power of lens? Pen is at 10 cm from concave lens. Find the location and nature of the image. Now, since it is a concave lens, the focal length is negative. So f is minus 10 cm. To calculate power of a lens, focal length is used in meters. So f is equal to minus 10 cm. Converting into meters, will divide with 100 minus 10 over 100 meters, which results in minus 0.1 meters. Now, since power of the lens is the reciprocal of the focal length in meters, so we write it 1 over f is equal to minus 1 over 0.1, which is equal to minus 10 per meter, or power of the lens is written as minus 10 d. D means diopters. Remember, power of a concave lens is negative. Now calculate di, the distance of image from lens when DO is 10 centimeter. Now again, using the lens equation, 1 over f is equal to 1 over di plus 1 over do. Since we need to find di, we make di the subject, and for doing this we calculate all this as we have done it earlier as well on the sidelines, and finalizing it, di is equal to f do over do minus f. So now putting it in the main body of the question, substituting values in this equation, we get di is equal to minus 10 into 10 over 10 minus 10, which is minus 10 over 10 plus 10. These two negative signs become positive and results in minus 10 over 20, which is minus 5 centimeters. Remember, sine of the distance of image is same as the focal length. This shows that both are on the same side of the mirror. Since image is not on the natural path of light, hence it is a virtual and erect image. Problem 7. Consider a convex lens of focal length 10 cm and concave lens of focal length 15 cm. Find the power of lens, power of both the lenses. This is a very simple problem. We have done it earlier as well. The power of the lens is reciprocal of the focal length in meters. So to find the power of a lens, the focal length must be in meters. For the convex lens, f is equal to 10 centimeters. Converting it into meters, 10 over 100 meters, which is equal to 0.1 meter. Power is equal to 1 over f is equal to 1 over 0.1 per meter, or it is 10 diopters. Power is 10 diopters for convex lens. In the other case, the focal length is 15 cm, that is for the concave lens, and it is a concave lens, its focal length is negative. So f is equal to minus 15 cm, converting it into meters, minus 15 over 100 meters, which is equal to minus 0.15 meters. Putting it in the equation for the power of the lens, that is reciprocal of the focal length, 1 over minus 0.15 per meter, or it is power is minus 6.67 diopters. Problem 8. An object is placed from a convex lens of power 10D, from where an object should be placed to get a 3 times real image, 3 times virtual image. So here we have two different questions. In one we need to find the distance of the object from where we can get a 3 times real image, and then 3 times virtual image as well. So we need to find the distance of the object to form a 3 times enlarged real image and 3 times enlarged virtual image given the power of a lens. Here we are given only the power of the lens. So to calculate the focal length of the lens, because we need focal length to calculate the distances of the object from the lens. So to calculate the focal length of the lens, we used power is equal to 1 over f, where f is in meters, which is equal to, or f is equal to 1 over p. Now this f is equal to 1 over 10 by substituting this power of 10d, and this is in meters, multiplying it with 100 results in 10 centimeters. So focal length of this lens is 10 centimeters. Now from the magnification, it is given as height of the image over height of the object is equal to magnification, or distance of the image over distance of the object is also magnification. Since here we need the distance of the image and distance of the object, so we use di over do, which is equal to 3, so which results in di is equal to 3 do. Now for a convex lens, remember, and a 3 times real image, do, di and f all are positive. Now substitute f is equal to 10, di is equal to 3 do. That's what we calculated here in the lens equation. Lens equation is 1 over f is equal to 1 over di plus 1 over do. So substituting these values, it becomes 1 over 10 is equal to 1 over 3 do plus 1 over do. We have changed this di into do using this relation. Now 1 over 10 is equal to, this 3do is the LCM of these two, 3do, and this results in 1 plus 3, and that makes it 1 over 10 is equal to 4 over 3do. Now solving for do, take do to the other side, cross multiply, and 10 to the other side, which results in do is equal to 4 into 10 divided by 3, which comes out to be do is equal to about approximately 13.3 centimeters. The same problem 8. Now this time we have to find 3 times virtual image, and remember, for a virtual image from a convex lens, the object has to be placed between the focal point and the lens itself. That means the distance of the object has to be less than the focal length, that is 10 centimeter is the focal length, so distance has to be less than the 10 centimeter. So let us see how it goes. Formula for the magnification, again the same formula, hi over h naught, di over d naught equal to the magnification. Since we need the distances, so we use only this di over d naught. I am taking this di as negative since it is a virtual image for a convex lens. The virtual image for a convex lens has a negative sign. Di, distance of the image has a negative sign. So it is minus di over do, which results in di is equal to minus 3 d naught. We will use it next in the mirror, in the lens equation. So for a convex lens, 3 times virtual image, di is negative, do and f are positive. Substituting f is equal to 10 di is equal to minus 3 do in the lens equation. So it is 1 over f is equal to 1 over do plus 1 over di. Substituting 1 over 10 is equal to 1 over do plus 1 over minus 3 do. This I have substituted for di from this relation, remember. Now, 1 over 10 is equal to 1 over do minus 1 over 3 do. This negative sign has changed this plus to minus here. And taking 3 do as the LCM and solving this equation, it becomes 1 over 10 is equal to 3 minus 1 over 3 do, which is 1 over 10 is equal to 2 over 3 do. Since we need to solve for do, taking do to the other side, the left hand side, through cross multiplication, and 10 to the right hand side. I am taking only do here, not the 3's where it was. So it becomes do is equal to 2 into 10 over 3, which solves to 6.67 centimeters. This is all for the numerical problems for chapter 12. Please subscribe to the channel if you haven't done yet, and share this video with others. And you may press the bell icon as well as the thumbs up. Thank you very much.